Yeah, so before we start today's class, so we'll just have a review of what we discussed in the last class. So can you tell me what we discussed in the last class? Okay, so we first discussed the forwarding conditions. Okay, so we came up with some equations which will detect when exactly to forward. So that was discussed, and when we discussed about forwarding unit and what will be the inputs to this forwarding unit and what will be the output. So can you tell me what exactly should I do at the input of ALU to implement forwarding? What units should I add, or what should I do at the input of ALU to implement forwarding? Do you get my question? So you have a EX stage, right? ALU or EX stage. So forwarding meaning you will be forwarding the value to the input of ALU or input of EX stage. So there you need to add multiplexers. Now, who will the multiplexers will typically have three inputs. One input could be coming from directly the register. The other two inputs can be forwarded values either from the output of ALU stage or from the output of MEMS stage. Okay. So that was what we discussed in the last class. So we'll just touch upon that and then we'll move on to today's topic. Okay. So we were discussing that the input of EX stage. So after this ID/EX register, so you will be adding a multiplexer. Specifically, you will be adding a 3:1 multiplexer, and the one of the input is directly from the register file. This input is from the register file, whereas this input and this input is from the output of this particular register x/mem register, where previously computed value will be available. Okay, so that value you need to forward, or in some cases you will be forwarding the value from mem/write-back stage. So if you forward from in the case of x hazard, we forward from the output of x/mem register. In the case of in the case of mem hazard, we will be forwarding the value from the output of mem/write-back register to the input of ALU. This forwarding unit, which will evaluate the condition. We discussed some conditions. So those conditions will be evaluated with the help of by taking all of these as inputs: ID/EX register RS1, RS2, and then mem/write-back register RD, EX/mem register RD, then reg-write signal. So all of that will be taken as input, and it will generate the selection signals for this multiplexer. We call it as forward RS1 and forward RS2. Each of these signals are 2-bit values, which will tell you whether the value is to be taken directly from the register file or whether the value is forwarded from some stage. Okay, so that information will be conveyed by these signals. We also have seen different cases of different possibilities where this could take 0, 0, 0, 1, 1, 0, and this also could take 0, 0, 0, 1, 1, 0. So all the possibilities we have, I think most of the possibilities we have discussed, if not all. Okay. So this was about the forwarding implementation in case of normal data hazard. But there are some data hazard cases where forwarding alone will not work. Okay, so an example of that is when you have load followed by a data dependent instruction. So S0 is basically a destination register in the case of load, and that is being used as source in the next instruction. So the problem in this scenario is when will the S0 value be ready? Okay, so that is what is important. So when you have an instruction like add S0, S1, S2, so the S0 value will be ready at the output of EX stage. Okay, at the output of EX stage, because you will be reading these two values and you will be doing the addition, and that added result will be there at the output of EX. But when will the S0 value be available in the case of load instruction? So where do you get the S0 value from? Where do you get the S0 value from? You'll be able to get the value of S0 from memory. So the value will be available here. If the value were available here, you could have directly forwarded. Okay, meaning you could directly forward so that the next stage will get the output. But if the value of S0 is available only at the end of this stage, end of one stage, whereas you want to compute the next instruction in here itself, so it will be a problem. Okay, so this way you will not be able to forward. Okay, you will not be able to forward in this case. So what you have to do, you have to stall the second instruction. Okay, by how many cycles? By one cycle you will stall the second instruction. That is as good as, and then you can forward. Okay, and then you will be able to send the value which is ready at the output of mem stage to the input of ex stage. Okay, so this delaying of second instruction is as good as adding a instruction in the middle which does not do anything. That is equivalent to adding NOP. Okay, so it is equivalent to adding NOP in between these two instructions. Okay, so we'll try to see how actually this happens in the case of pipeline processor. We'll do the analysis just like we did in the earlier case. We'll assume a pipeline structure like this. Okay, we'll assume some initial values for S0, S1, and S2. We'll also assume that the memory location that I'll be using is 20, and the value that is available in that memory location is 5. Okay. Now let us assume some instructions. Okay, so here there is a data dependency of on S0 in this instruction as well as in this instruction. Okay, S0 value is being computed by load, and that value is being used in add S3, S0, S2 instruction, and also in the add S4, S0, S1 instruction, S0 value is being used. Okay. Now let us see where the problem comes, and based on that, maybe you can try to come up with the equation for detecting this condition. Okay, detecting the case where you have to stop. Okay, so let us see stage by stage what happens. So at the end of first clock cycle, again we'll assume that S1 plus 20. We are assuming S1 is 0. Okay, so and if you are actually doing S1 plus 20, then the address will be pointing to 20, and the value that will be there in that particular memory location is 5. Just for example's sake. Okay. Now, at the end of clock cycle 1, you know that the information related to first instruction is already loaded in IF/ID register. So the relevant information is your RS1, which is source 1, is S1. Here RS2 field will not be used. Okay, but you still will have some value in RS2, which is like some other information, but it is not related to the second source register. It is some other information that will be there in the load instruction. If you can recall the instruction code for load, you will understand. And then you have the destination register, which is S0. Okay, so this is what happens in the first clock cycle. Now in the second clock cycle, what happens? So in the second clock cycle, at the end of second clock cycle, you will be reading the value which is S1. Okay, you'll be reading the value of S1, which is 0. And you will also be reading some register because RS2 field is not empty. It might contain some junk value. Okay, but according to that, some value might be read. So you can consider some value will be coming here, but it is not important. Okay, you have to, who will make sure that the correct value is sent to ALU for address calculation? In addition to that, the 20 will be sign extended, and that will be available here. So here, whatever value will be there, this value will not be passed to the ALU. Rather than like instead, 20 will be passed to the ALU for address calculation. That will be taken care by the MUX with ALU source as the control signal. Okay, so that will make sure that 20 is passed for the ALU for address calculation. Okay, so that is why you have been loaded with RD is available here. So first source is available here, and some junk value will be available here. Here again, it is not important value. This is some junk value, let us assume. And 0 is S1, and 20 is the sign extended value equivalent to the displacement that you have provided in the instruction. Okay. And at the same time, at the end of clock cycle 2, the second instruction will be loaded into the IF/ID register, or the information related to second instruction will be loaded into the IF/ID register. So till this point, no problem at all. Okay. Now the problem starts coming in the end of third clock cycle. So at the end of third clock cycle, what happens? So ALU would have calculated the address. It would have taken the S0, S1 value, and it would have actually added it to 20, and it would have calculated the address. The destination register is S0, but the value is not S0. Okay, so this is basically address, not the value itself. But here S0 is already being read. Okay, so S0 is being read as 1. Is this correct? S0 is being read as 1. Is this correct? So instead of 1, what should be passed as the S0 value? So 1 is not correct. So instead of 1, 5 should be passed as S0 value. But do I have the value 5 anywhere till now? I'm just passing the address 20. I have not read the memory yet. Okay, I have not read the memory yet. I'm just passing this address. So I don't have the value of S naught ready. Okay, the value of S naught is not ready yet. Now, if I continue without doing anything, if I just keep on executing, okay, so what will happen if I just keep on executing and uh, go to the end of clock cycle 4? One thing, can you tell me, will some condition get satisfied here? So you say that there is this as the destination and this as a source, right? So this destination is matching with this source. So do you mean to say I should forward the value to the ALU? Should I forward the value to the ALU? Should I forward 20 to the ALU? Reggerite is not one. Are you sure Reggerite is not one for this case, for this instruction? This is load, right? So the Reggerite is one. So your forwarding condition is getting satisfied now here. Will it create a problem? Value comes from data memory, that is correct. But what did you derive the conditions as? You just derived the conditions as a destination register is S naught, a source register you check. Um, so X hazard condition is satisfied, right? So how should I make sure that, how do I modify such a case? So here only we have to do the something. Okay, so the earlier conditions we will not change, but whenever the load is there, load instruction comes, we'll try to avoid this particular case here itself. Okay, but let's not come to that. We'll derive the condition first or little later. But you know the problem, right? So at the end of clock cycle 3, your S naught value is already read as 1, which will create a problem. Okay, if I don't do anything, if I go to the next clock cycle, what happens? The S naught value will be taken as 1, S2 is 2, and S3 will be calculated as 3. Okay, is this correct value? No, it is not correct value, so this is incorrect. So wrong values will start propagating for the S0. Okay, so this is an issue. So now you tell me, when should I detect this condition? So there is this data dependency on S0. Okay, so if I start, if I don't do anything, you know that there will be a problem. Okay, at this point itself, you will be a problem, because at this point itself, what happens is your 20 will be forwarded to the input of ALU, because your destination register is same as your source register, and all your previous conditions are getting satisfied. So your 20 will be passed to the ALU and it will calculate 22 rather than 1. Okay, so from clock cycle 2 itself, there is a problem. So what should we do? Where should I detect the problem and where should I solve the problem? So this is a clearly an hazard. So we are facing the difficulty because the value of S naught is not ready yet, and instead of 5, your value of S naught will be read as 1. So it will create a problem. Okay, so that is the reason you have to detect this and stall. Okay, stall the previous instruction. So you should not. You should. One thing is how to avoid this case. How do you avoid this case? You maintain enough distance between these two instructions. How much distance should I maintain? Now the distance between these two instructions is 0, meaning this is a, if I say this is one instruction, there is no instruction in between. Okay, so we still have to maintain a distance between these two instructions by 1 clock cycle. That is as good as keeping a stall. Okay, so when should I detect this condition that there is a load instruction with a destination register which is same as source register in the next instruction? So that detection I have to do, and based on that I have to stall. You tell me, when should I detect? Should I detect it at the end of clock cycle 1? Should I detect it at the end of clock cycle 2? Or should I detect it at the end of clock cycle 3? So at the end of clock cycle 3, anyway, you can't wait till end of clock cycle 3, because this condition, the earlier condition, is getting satisfied and the 20 might be sent. So this is too late. So when is the earliest that I can detect this condition? When is the earliest that I can detect this condition? So at the end of clock cycle 2, okay, so that is correct. So we'll see how exactly that happens. Okay, so we saw the problem. Now we'll try to find the solution. Okay, so at the end of clock cycle 1, not a problem. Only the first instruction is getting loaded here. Load s naught comma, and the information related to that will be available. Now at the end of clock cycle 2, okay, at the end of clock cycle 2, you have the value of s naught, sorry, value of s naught, s1 as 0, and 20 will be passed to the ALU, and the destination register is s naught. So all of the information is loaded here. And the next instructions information is available in if/id register. Now, as we have discussed in the previous slide, I can't wait for third clock cycle. I have to do something here itself. Now you tell me, first thing, how do I detect this condition? Okay, so what should I do to detect this condition? And then we'll talk about how to stall. So can you identify how do I come up with the equation to detect this case? Check for, should I check for the entire opcode? So you're saying that first thing I have to check is, I have to check whether the first instruction is load instruction. Now, how do I check whether the first instruction is load instruction? Should I check opcode? Should I check opcode? But then the opcode for load word, load byte, load half word. Okay, so for all of these, the opcodes might be, I think, opcodes, I think will be same for all of them. So in that case, should I detect opcode? Should I detect function code? Is there any signal which is unique to load? See, for all of these cases, you might still have to do that. Okay, you still have to, there will be still data dependency. One thing is you can check the opcode, but opcode is 6 digits, no? So instead of 6-digit comparison, can I come up with a signal which will directly tell me whether it is a load or whether it is load or not load? Can you tell me one signal which will be one control signal which will be 1 for load instruction, and it will be 0 for all other instructions? So that, as some of you have suggested, so that is memory read. Okay, only in the case of load instruction you will be doing memory read. Okay, so you have to basically check whether the memory read signal is equal to 1 or not. Okay, so can you tell me further? So first thing I'll do is I'll check memory read, but which memory read? That also you should be clear, because there might be many memory reads depending on many instructions that are available in different stages. So you have to check for id/ex memread, okay, if it is equal to 1, okay, and what else? What else should I check for? This case, right? So whether your id/ex dot rd, the destination register of the instruction that is available in id/ex register, if it is equal to if/id rs1 or rs2. Okay, so or again you can write it in different terms, or id/ex dot rd if it is equal to if/id rs2. Okay, so this is the condition that I have to detect. So this will tell me that there is a dependency. Okay, so this is to just detection part. Okay, once you detect the condition, what should I do next? Once you detect the condition, what should I do next? I have to stall the pipeline. Okay, now stalling the pipeline, what does stalling the pipeline mean? Okay, so that I am showing you. So stalling the pipe, this was the earlier case. Now let's say your condition is matching. So your destination here is matching with the source here, and your memory signal for the load instruction is 1. So hence the condition is matching. You have to stall. Now what do you mean by stall? Okay, that you have to understand. The meaning of stall. Okay, so stall occurs after this instruction, right? NOP is like when you want to stall, it's like adding NOP between these two. That means this at the end of next clock cycle, that is at the end of clock cycle 3, this instruction should move forward, whereas this instruction should remain wherever it is. Okay, so that is what you mean by stall. In that case, there will be an empty slot here because this instruction will be going on to the next stage. and this instruction will stay back here. Now there will be an empty slot here. So that I have to fill up with some information which is equivalent to NO. Okay, so that is what you mean by stall. So if this condition is getting satisfied, you see that load instruction is moving to the next, load instruction is moving to the next pipeline stage, whereas add instruction will remain at the same prevent PC source from incrementing. We'll come to that. It's not just PC source incrementing. There are other things that are involved. Okay, we'll come to that a little later. But here I'm just showing you how the instruction progress will happen. So this instruction will progress, whereas this instruction will remain the same. Okay. Now, what happens at the end of fourth clock cycle? At the end of fourth clock cycle, now the value of S0 is ready. Okay, the value of S0 is ready, which is 5. And in between you had an NOP, so nothing will be available here. No valid information will be there. And this instruction, the second instruction, is now available in ID/EX stage. You still need forwarding, right? When load is followed by add instruction, stall alone will not work. Okay, stall alone will not work. Stall plus forwarding you have to do. So in that case, should I come up with separate equations for forwarding? So this is at this stage, should I come up with separate equations for forwarding, or is it already taken care of? So what equation will take care of this forwarding? X hazard condition or mem hazard condition? The mem hazard condition will already take care. How will it take care? So if you see, the reg write signal for this is load instruction will be equal to 1. So one part is getting satisfied. The destination register, which is S0, is equal to the source register of this instruction. So that also is getting satisfied. So what you do at this point is you send the value which is already ready to the input of ALU. So instead of 1, 5 will be sent to the ALU for computation. Okay. So remember, whenever there is a load followed by data dependent instruction, so first thing is you have to separately check for stall condition, which we just derived. Okay, stall condition you have to check. In addition to that, you have to forward. But this forwarding part is already taken care by the mem hazard condition, which you had implemented earlier. So it's not that you implement both of them separately. Okay, so entire unit will have forwarding unit as well as stalling unit. Both will be together. Although in the next figure, when I show the hardware, I'll show one unit alone. But don't assume that only one unit will be there. You should assume that both units will be available for normal working of the pipeline without any hazards. Okay. So this is how we will stall, and once you stall, the forwarding will be automatically done with the help of previous instructions. Okay, and then so this is the condition that we derived. So ID/EX memory is equal to 1, and ID/EX register RD if it is equal to RS1 or if it is equal to RS2. So in that case, in that condition, I have to basically stall the pipeline using NOP. Now, what do you mean by NOP? What is it equivalent to? It is equivalent to stopping the clock for PC and IF/ID register. Okay. So when you want the pipeline register to not change, okay, whenever I said that I add instruction will remain in that pipeline register only, okay, that basically means that this register should not change. So there is some input data available, but the output data should remain as it is. So in that case, what you do, you basically stop the clock. Okay, so that is one thing. So you have to stop the clock for PC and IF/ID register, and you have to make all the control signals for that NOP instruction that you are adding in the middle as zeros. Okay, so if you just see how the implementation will be, so control unit will generate the control signals, but in addition to that, you add a multiplexer here. Okay, but you have the stall or hazard detection unit, which will take ID/EX memory signal, ID/EX RD signal. It will also take the IF/ID register RS2 as well as RS1 as inputs. Now it will produce some outputs. Can you tell me what will it produce as the outputs? It will produce, let's say, some signals. Okay, it will produce some signal, let's say IF.write. It will also produce a signal called as PC.write. In addition to that, you have to make sure that the control signals are zeros for that particular instruction. So I'll put a multiplexer here, and instead of sending the normal control signals corresponding to the instruction that is available here, okay, I'll have to send all zeros. So can you tell me what is the advantage of all zeros? What do you mean by all control signals being zeros? What will happen? So although logically speaking, when I say NOP, you can think of instruction like add 0, comma 0, comma 0. Okay, that is like a logical equivalent of NOP instruction. But what exactly do you mean by control signals being 0? So when you make control signals 0, okay, so let me put it in another way. What are the major operations that might happen in the processor? What are the major operations that might happen in the processor? There are three major operations, okay, which may alter your execution. Can you tell me what are those? No, I'm not talking about instruction. I'm talking about operations. Okay. So when I say something is getting modified, let's say your register is being written into, that is one modification that might happen. Or your memory might be written into, that is one thing. Or your memory might be read unnecessarily, even though you don't use it, your memory might be read unnecessarily. So these are the major operations: your memory read and write, as well as your register write. So you have to avoid those. So the best way to avoid those is make the control signal 0. If your write is 0, nothing will be written into the register. If your mem read is 0, nothing will be read from the memory. And if your mem write is equal to 0, nothing will be written into the memory. So that is as good as no operation happening. So hence we say that the control signals will be made 0, and then it will be sent whenever you want to stall, whenever the detection happens here. Okay, what you do is you just stop the contents of these two registers there only, and you send 0 as the control signals for the next case, and the load will normally pass the control signals corresponding to that. Okay, so that is how the stall condition is implemented. Now tell me, how is this implemented internally? So when I say I want to generate PC write, IF write, like internally, how it might look? Okay, let's assume there is a register, or let's assume there is a 1-bit register. What is a 1-bit register? What is a 1-bit register? A D flip-flop. Okay, let's say there is a D as input and then Q as your output. So Q gives whatever value is stored currently, and then there is this clock. Okay, let's say this is corresponding to PC. This flip-flop is corresponding to PC, and it has already been loaded with some address. Okay, and then let's just assume there is one more register, which is your IF/ID register, and here also some information is loaded. There is another flip-flop. I'll assume only 1 bit. You can extrapolate it to whatever be the size of this pipeline register, and then there is clock. Okay, so this is corresponding to PC, and this is corresponding to IF/ID register. Okay, so now when I say I want to generate PC write and IF write, can you tell me how do I include that within this register? So the purpose of IF.write and PC.write is your output value should not change. Your output value should not change. If this is the output value that is available for PC and this is the value that is available for IF/ID flip-flop as IF/ID register, so those values should not change. Feed Q back to D with a mux. Yeah, but is there a better solution? And that is one solution. So again, as we discussed in the previous slide, what we would like to do is we can send something like this. So we can send the normal clock through an AND gate, okay, and the PC write signal. Okay, so let's say PC write signal, I'll send it through a NOT gate. So if PC write signal is equal to 1, what will it do? I will come to that. Clock gating is undesirable, but again, in some cases you can't avoid it. It is undesirable. That though is for sure. So what will happen when PC write is equal to 1? So depending on the condition, if the stall hazard detection unit will generate PC write is equal to 1. So what happens if PC write is equal to 1? The clock is equal to 0. So even if there is a positive edge of clock seen on the original clock, this clock will not see this positive edge because PC write is 1, meaning 0 will be given as input to this AND gate, and this output will always be equal to 0. So in that case, this value won't change. The same is with the IF/ID pipeline register. So the main purpose of this IF dot write and PC dot write is to make sure that the instruction will remain there only. Okay, the instruction will remain there. Okay, whenever you want to stop. Okay, but some data corresponding to this value will move to the next pipeline register when you go for when you go to the next clock cycle. So some data will start moving here. But how do I make sure that there is no effect of this? It's all when I say that some data is already available in IF/ID register, you still might read some registers and some data might get loaded into this pipeline register. But how is that getting avoided? How do I reduce the effect of this? What will make sure that even though some information is passed, so that will not affect the overall execution? That will be taken care by this part. That will be taken care by the control unit. Instead of sending the normal control signals, you pass 0. Okay, then the instruction will not have any impact. Okay, so what I'm trying to say is, if I go back to my earlier explanation of moving, okay, so at this point, okay, or rather, let's say, so this was the condition. At this point, you detect. Okay, so at this point, you will be detecting the hazard because all of the conditions are matching. So once I detect the condition, I'll make sure that this instruction stays as it is, and PC will be loaded with some address. I want to make sure that that is also there. So I'll stop the clock for this, stop the clock for this. But at the end of next clock cycle, right? At the end of next clock cycle, the S0 value is being fed to the register file. The S2 value is also being fed to the register file. So some values will be read. Okay, for example, in this case, S0 is 1, so 1 will be read, and S2 is 2, so 2 will be read. So when at the end of next clock cycle, so you will get 1, 2 here, and your ALU might do some operation also. So even though I say NOP, some data is also being sent, right? Okay, so how do I make sure that the effect of this is not there on the overall execution? That can be done by sending all of the control signals as zeros. If I make all of the control signals as zeros, whatever data you send, that will not affect the overall execution. Okay, so that's the reason I have to additionally send the control signals as zeros in the hardware part. Okay, I have to send the control signals as zeros. So this detection unit basically sends 3 signals. One is to stop PC from changing. One is to stop IF/ID from changing. The other is to send 0 for the NOP instruction. All the control signals are 0 for the NOP instruction. So that's the purpose of these 3 signals. Okay, so this was all about the discussion of data hazards. So at this point, maybe I'll take a couple of minutes to see if you have any doubts. Okay. Do you have any doubts with respect to data hazards? Remember, again, as I said earlier, it's not that only hazard detection is available. There is a forwarding unit also available here. Okay. Okay, so both should be available for your pipeline processor to work. Okay, so if you have understood this part, the data hazard part, so let's move to the control hazard. Don't you have to check for? That's a good question. So shouldn't we check for whether the load inspection is changing 0? So we derived some condition, right? So we derived this condition. Okay, so should we add something here? What if it is a 0? So what if it is a 0 and if there is a data dependency, there might be unnecessary stall. Okay, so again, if you anyway, mem hazard will take care of it, but mem hazard will take care of it when? When will the mem hazard take care of it? After stalling. Okay, so that is after stalling. So if this is a zero register, then you are stalling unnecessarily. Okay, so if you don't want to stall unnecessarily, then you can add one more condition. Although your textbook does not discuss it explicitly, it's good that you have pointed it out. Again, it's an uncommon case. Even this is an uncommon case, right? Add 0, comma s naught, comma s1. Why do you want to have a destination of 0 when you know that 0 can't be changed? We still discussed about this when we are talking about X and mem hazard, right? So it's like same thing. Okay, so whenever you want to, whenever you have this 0 as the destination for load instruction, you don't want to stall unnecessarily. Isn't that 0, comma s naught, comma s standard NOP instruction? Again, standard NOP instruction, yes, that's correct. No, what was your question related to that? No, I was explaining for the earlier case. Anyway, in this case, we detect this condition and we avoid forwarding in the X hazard and mem hazard case. But load into 0 register is wasting lots of clock cycles if it has to fetch data from data memory. Again, we are all talking about optimization. Okay, so first thing, okay, so if you want to avoid stall, you can detect whether id slash ex dot what should I say, rd, if it is not equal to 0. Okay, so that condition also you can add to be ideal case. Now people are talking about if it is 0, then the load instruction will unnecessarily access data memory. Okay, so that is like one more level of optimization. Now, if you don't want to access data memory, if the instruction is load, then you have to come up with some other condition, additional condition when the instruction is there in ex slash mem. Okay, so what you can do is if ex slash mem, okay, dot mem read signal is equal to 1, but ex slash mem, okay, register rd if it is equal to 0, then what you do, you still make your memory signal as 0. Okay, instead of passing this as memory signal, you pass 0 as memory signal. So that way you will avoid unnecessary data memory. So that is like optimizations. Okay, maybe if I keep on discussing all of these optimizations, things will become very complex. Okay, so one optimization that is possible here is to check for to avoid unnecessary stalls. You can check for destination register whether it is equal to 0 or not, and then avoid the stall altogether. Okay, you stall only if it is not equal to 0. If it is equal to 0, you don't have to stall it all. If you're talking about unnecessary access to data memory, then you can add one more condition like this, but that is like a separate control unit will be there just before the memory, which will check if the memory signal is 1, meaning whether it is a load instruction. But if the destination is 0, then what you do, you make your memory signal as 0, so that will avoid unnecessary data memory access. Okay, is it clear? So did I answer your cases, both of your cases? Okay. So let me move on to the control hazard. We have already discussed the conceptual concept related to structure, control hazards. You know when the control hazard occurs. So the control hazard occurs mainly with respect to branch instructions. So normally when you execute branch instructions in a pipeline, you expect that the next instruction, the evaluation of the condition will be done only at the end of EX stage. So the next instruction should start fetching only after this. Okay, that is as good as including two NOPs or wasting 2 clock cycles. What was the solution for this? What was the solution for this to avoid the stall? What was the solution that we came up with? Prediction. Okay, so we came up with branch prediction. A simple branch prediction, how it happens, you know already. Not forwarding, branch prediction. Okay, so this is with respect to control hazard, right? So in this case, you start, if it is not taken scheme, you start fetching, in this case, you start fetching this next instruction. If the prediction is true, you don't do anything. But if the prediction is false, okay, if the prediction is false, then at the end of EX stage, you will know whether the condition is true or not. So at that point, you have to flush. Now this, how it should happen in the hardware. What pipeline stages should I flush? Okay, and what exactly do you mean by flush? Okay, so those things we can actually see in the next few slides. So normal prediction true case, you don't have to do anything, but in the prediction false case, you have to flush and you have to start fetching the correct instruction. Okay, so how it is handled typically in the case of hardware, we'll just try to visualize. We'll not go into the exact implementation details. We'll just try to visualize how it actually happens. So for this case, initial case, I'm assuming that the branch condition is evaluated at the output of ALU. Okay, and you have this as the pipeline stage. So since PC is also important for this case, I'm showing PC also for control hazard. Okay, so at the end of clock cycle 1, again similar to our earlier analysis, we'll try to see what happens at the end of each clock cycle. At the end of clock cycle 1, your first instructions information will be already there in IF/ID register. Then can you tell me at this point what will be there in PC? At this point, at the end of clock cycle 1. At the end of clock cycle 1, I said that IF/ID will get loaded with the first instruction. If that is the case, can you tell me what will be there in PC at this point? What will be there in PC? Meaning, what do you mean by PC plus 4? So here we are talking about instructions, right? So what will PC have? The next instruction address. So what instruction address? So in this example, what will PC have? In this example, so it will have the address of this location. Okay, so it will have the address of add S3, S0, S1. Okay, so that is important to understand. So at the end of clock cycle 1, the first instruction gets loaded in IF/ID register. Okay, at the same time, your PC will get loaded. So if I start PC with this, then PC will get loaded with PC plus 4 at the end of clock cycle 1. So meaning your PC will have the address for next instruction, which is add S3, S0, S1. Okay, so I'm starting. Here I'm assuming the not taken scheme. Okay, but normally if you implement branch prediction, what will you do? If you implement branch prediction, what will you do? What will you do if you implement branch prediction? So here though, since I'm assuming not taken scheme, I'm directly fetching the next instruction and PC is loaded with the next instruction address. Okay, so if at all, so what you have to do is that branch history table, you have to keep it in the IF stage itself. Whenever it sees that there is an instruction called as branch at the output of at the output of the instruction memory, what it will do is it will separately calculate the PC based on the prediction and automatically loads the PC with either the next instruction or either the next instruction, that is PC plus 4, or the instruction where the jump should happen, where the branch should happen. So that is PC plus 4 plus X. So that will be decided in the IF stage itself, and PC will get loaded accordingly. So here, since we are assuming a simple case of not taken scheme, okay, not taken scheme we are assuming. So I'm assuming that the PC is having next instruction. Okay. So what happens at the end of clock cycle 2 then? So at the end of clock cycle 2, your branch instruction will move to ID/EX stage. You keep fetching next instructions. Okay, there is no change. You keep fetching next instructions, assuming your prediction is true. So in that way, IF/ID will get loaded with this instruction, and then your PC will have the address for sub instruction. Similarly, at the end of clock cycle 3, your BEQ is coming here. Now your add instruction is in ID/EX, and sub instruction is there in IF/ID. So at this point, because now that you have evaluated, because now it is already evaluated and getting loaded. So at this point, you will know whether your prediction is true or false. Now, if your prediction is true, not an issue at all. Okay, you can carry on with your execution. But at this point, your outcome has come. Okay, your prediction, you had predicted something. Okay, now you will be able to check whether your prediction is same as your, that is, you'll be doing an XOR operation kind of a thing, whether it is XOR rather. So your your prediction, whether it is same as outcome, you'll be able to check now. If it is same, if your prediction is same as outcome, you don't do anything. Now, if your prediction is false, what should I do? What should I do if my prediction is false? Flush. Now you tell me how many resistors should I flush? How many resistors should I flush? So first thing you have to flush is, if the prediction is true, no problem. Else, you have to flush this instruction that is there in id/ex. You have to flush this instruction, which is there in if/id. Is that enough? Is that enough? What is with PC? So at the end of clock cycle 3, PC will have this address, the address of add a instruction. So that also you have to flush. Okay. So you basically have to flush 3 registers, okay, 3 register contents. So one is your if id/ex, if/id, and then you have to flush whatever address is stored in PC. Once the flush is done, then you can. So flushing is again making control signals as 0. That is as good as making the control signals of those cases as 0. Okay, make the control signals in id/ex as 0, and similarly you have to change the information that is available in if/id register such that it gives a equivalent of NOP instruction. Okay. But at the same time, once PC gets flushed, what should PC change to? So you flush here by adding some equivalent instruction to NOP. So here you flush by making control signals as zeros. But what will you do with PC? What will you do with PC? You change PC to what value? You change PC to the target address. By the time the branch instruction is loaded in ex/mem, your target address would have been calculated already. So that you will be loading it in the PC register. You still have to flush, and then you will be loading the updated value. Okay. So if this is a problematic thing, because your evaluation is being done only at the end of EX stage. So there is some optimization possible. Now we'll try to see if optimization is done, whether I'll be able to put in less effort. So one optimization that you can do is you can move the branch execution earlier in the pipeline. This involves 2 things. One is you move the block which computes the target address earlier. The second thing is you evaluate the branch decision much earlier. So that can be done by exploiting the fact that equality checking is simple. What do you mean by equality checking is simple? How do you check whether A1, B1, sorry, A1, A0, if it is equal to B1, B0? Let's say this is number A, this is number B. How do I check whether they are equal or not? Subtraction is a complicated operation. I need to check for equal case only. So when you want to check for equal case, you just XOR both of them. Okay, if the XOR result is 0, then both are equal. If the XOR result is not equal to 0, then both are not equal. So it's a simple XOR operation. Simple bitwise XOR operation will tell you whether they are equal or not. You will not be able to know the greater or equal to, less than. So those will require much more complex comparator. Okay, but at least for BEQ case, you'll be able to do it with a simple XOR. That's why in MIPS, in MIPS, there is no instructions like BG, BLT. Okay, all of these instructions are not there. Only 2 instructions are there in MIPS, BEQ and BL. So that way your branch implementation becomes much simpler. In RISC-V, of course, they have added all of these, branch if greater than, branch if less than. So that way your comparison becomes much more complex if you want to move it earlier. But if at all only BEQ is there, so that can be implemented with a simple XOR gate. Okay, you can exploit the fact that equality checking is simple. So what you do is, this was the earlier data path. What I'll do, I'll change it such that I'll be able to compute the address much before. You see. So here I was taking from EX/web register, but here I'm taking it much before ID/EX register only, because I'm including a special comparator here, which can just take the register content values, and you will be able to know whether both are equal or not. Okay. Now, if this is the case, now we'll see how exactly things happen in the case of control hazard. So again, same case, at the end of clock cycle 1, your branch is available here. Okay, at the same time, if you are assuming not taken scheme, the PC will have the address of this instruction. So can you tell me at the end of next clock cycle what will happen? At the end of next clock cycle, what will happen? So your comparator is put much before ID/EX register itself. The comparison will be done, and you will know the condition. You'll know whether the registers are equal or not before even loading into ID/EX. So what do you think will happen in the end of clock cycle 2? So at the end of clock cycle 2, because we are already feeding this, the comparator is already working. Okay, so at the end of next clock cycle itself, you will know the condition for comparator. Okay, so in that sense, what happens is by the time the next clock cycle ends, the end of next clock cycle, your next instruction will be available here. The BEQ instruction will be available here, and add instruction would have changed to IF/ID. But before even this happens, the comparator would have told whether both of the registers are equal, and accordingly, this marks would have selected the correct PC. Okay, what will happen at this point is the correct PC would have been loaded. If the condition is true, then the PC would have been loaded with this instruction, the sub instructions address, or the PC would have been loaded with this instruction address if the prediction is false. Okay, so that way, how many registers I have to flush now in this scenario? By putting a comparator before just after the register file and putting that address calculation unit much before ID/EX register. Okay, so what you will be able to do is you'll be able to optimize. At this point, how many registers should I have to flush? How many registers should I flush? Two? Can you think about it? Little more detail. You analyze the code. Okay, analyze the code. Analyze the data path that I have just showed. Okay, earlier this was the case. I was able to calculate the target address at the end of EX/mem stage. I was able to know the branch condition at the end of EX/mem register. Okay, so that is why it was taking more time, and PC was having some other value. You had to flush this instruction, this and this. But now I am moving my address calculation before ID/EX register. It is not getting loaded into the ID/EX register itself. So before only I will be able to compute the address. Okay, address will be calculated, and this mux you will be able to calculate the correct. This mux will be able to select the uh, correct address based on this condition. Okay, based on this condition. So in this case, if you see at the end of second clock cycle, this value is already loaded. By that time, Mux would have already selected the correct PC. In that case, PC would have the correct value. Again, if the prediction is false, it would already have the correct address, correct instruction address. So in this case, the only register that you have to flush is IF/ID. Okay. So this is a slight optimization. Again, it's still as good as including one NOP. In the earlier case, it is as good as adding two NOPs. But here, the flushing part you'll be doing only with one register instead of three registers. Okay. I think with that, I am done with this part. Okay. So this is one of the very important topics, understanding of pipeline processor, understanding of hazards in pipeline processor, and understanding the hardware required for implementation of pipeline processor is very important with respect to placements. I've been told by many of your seniors that they go in depth. Okay, so till the depth that we have discussed in class, so till that depth they keep asking the questions. If you have listed, if you list whatever I will be giving as assignment, so if you list that assignment as your as one of your projects, then you have to have a very clear understanding of all of these pipeline processor concepts. Okay, so what do you mean by data hazard? How do you resolve data hazard? What exactly do you mean by forwarding? How is it implemented? When do you stall? How do you stall? Control hazard. How the what how do you exactly solve control hazards? How is it implemented in hardware? Okay, how do instructions move from one stage to another stage? So all of that you have to have in-depth knowledge if you say that you know pipeline processor. Okay. So with that, we have completed one of the major topics of computer architecture. So now from next class onwards, we'll be starting again as per the handout. I'm supposed to start with floating point arithmetic. Anyway, integer arithmetic I had given it as a reading assignment. This is like how are adders implemented, how is subtraction implemented, division, multiplication. Okay. So all of these you already studied as part of digital design. If you have not, I'll be uploading the slides. You can go through the slides. Okay. So there are many division algorithms, right? Do you know any division algorithms? What are the division algorithms that you have gone through? Multiplication, you have serial multiplier, parallel multiplier, basic multipliers, and then you have booth multiplier. So similarly in division, you have, do you remember division algorithms? Restoring, okay, non-restoring. Okay, so all of those things you have either studied as part of what do you say, as part of digital design or as part of microprocessors. So that I am directly giving as reading assignment. As part of this course, you are supposed to discuss floating point arithmetic, but I feel that this is like slightly different and it might affect our course flow. So what I'll do is for this I'll upload the slides. Okay. If you are okay with it, for floating point arithmetic, I'll upload my last year's videos. Okay, I'll upload my last year's videos. Okay, so you can go through that and you can try to understand what exactly is floating point arithmetic. So here they talk about floating point representations, which is IEEE 754. Okay, so it's a standard representation. So there are two formats, 32-bit, which they call it as single precision, okay, and 64-bit, which they call it as double precision. So how exactly the numbers are encoded as 32-bit floating point number or 64 floating point number? How do you convert a decimal value to standard floating point format? Okay, all of that is discussed in the class. Okay, so if you have already covered that, then it is fine. It will well and good. So what I'll do is I'll not be teaching this separately now. So I'll try to upload the videos for it. Okay, so again, it is not, everything is clearly explained in the videos. If you have any doubts at any point, you can always talk to me, okay, and I'll clarify those, okay. So it's a simple topic, and I think it disturbs our discussion, okay, because it's slightly a different topic than what we are discussing. So I'll upload the videos, lecture videos for floating point arithmetic, so you can go through those, okay. But in the from next class onwards, what I'll be discussing as part of regular lectures is memory concepts. Okay, memory organization will be starting, where we'll be discussing about cache, then virtual memory. So instead of spending time on this, I feel that if you spend more time on understanding memory organization, it will be very helpful both in placement perspective as well as your understanding of computer architecture perspective. Okay? So that's the reason I'm giving these two as assignments. Integer arithmetic, I'll just upload the slides. I'll not upload the lecture videos. For floating point arithmetic, I'll upload the lecture videos. Okay. So with that, I'm done for this class. If you have any doubts, please feel free to ask them. If you don't have any doubts, then thank you. Okay, so which data path? Modified data path? So it's like this will work when the comparator has very less delay. Okay, so very less delay if it has, because it's only one XOR gates that will come into pipeline path. When you compare with overall register delay, overall register file delay, this is very negligible. So this is as good as included within the register file itself. So it will not take much time to know whether both are equal or not. That's the advantage that we are trying to take. Would we be using wrong PC for target calculation in this case? Why wrong PC?
Sir, by the time the branch is in the higher stage, the PC has changed.
Branch is in the ID/ex stage.
Either whether it is an ID or IF, the PC has changed anyways before the comparator calculates.
It is still going through pipeline, no? It's still going through pipeline. This IF/ID register is still going through pipeline.
Okay, so the PC is pipelined in the IF/ID.
PC is pipeline in IF/ID. When I show signal like this, if I had to show without pipelining, then I would have showed signal something like this.
Okay, okay.
Okay. So when I show through this, it is passing through the pipeline register.
Okay.
Okay. Earlier, what happened if you just observe? Okay. Earlier, if you observe, so it is still going through both the pipeline stages. Only then it will be correct. Otherwise, it will be wrong. If your PC you don't set, excuse me. So if PC, if it is not sent through the pipeline stages, we give you the wrong answer. So PC is sent through the pipeline stages to calculate the correct address, which is like PC plus some first step. Okay. Okay, I think if there are no doubts, then that's all from my side. Thank you.